Hello, good day. Today we will talk about database normalization. Database normalization is the process of structuring a database, usually a relational database, in accordance with a series of so-called normal forms in order to reduce data redundancy and improve data integrity. It was first proposed by Edgar F. Codd as part of his relational model. In relational database design, the process of organizing data to minimize redundancy is called normalization, or the process of decomposing relation with anomalies to produce smaller, well-structured relation. Normalization usually involves dividing a database into two or more tables and defining relationships between the tables. The objective is to isolate data so that additions, deletions, and modifications of a field can be made in just one table, and then propagated through the rest of the database via defined relationships. Normalization is a process of decomposing a set of relations with anomalies to produce smaller and well-structured relations that contain minimum or no redundancy. The basic objectives of normalizations are due to reduce redundancy, which means that information is to be stored only once. Storing information several times leads to wastage of storage space and increase in the total size of the data stored. Normalization provides the designer with a systematic and scientific process of grouping of attributes in a relation. The normalization process can be defined as a procedure of analyzing and successive reduction of the given relational schemas based on their FDS and primary keys to achieve the desirable properties of minimizing redundancy, minimizing insertion, deletion, and update anomalies. The objectives of normalization process are 1. To create a formal framework for analyzing relation schemas based on their keys and on the functional dependencies among their attributes. 2. To free relations from undesirable insertion, update, and deletion anomalies. 3. To reduce the need for restructuring the relations as new data types are introduced. 4. To carry out series of tests on individual relation schema so that the relational database can be normalized to some degree. When a test fails, the relation violating that test must be decomposed into relations that individually meet the normalization test. The main goal of database normalization is to restructure the logical data model of a database to eliminate redundancy, organize data efficiency, and reduce the potential for data anomalies. First normal form. First normal form is a property of a relation in a relational database. A relation is in first normal form in the domain of each attribute contains only atomic values, and the value of each attribute contains only a single value from that domain. First normal form is an essential property of a relation in a relational database. Database normalization is the process of representing a database in terms of relations in standard normal forms, where first normal form is a minimal requirement. first normal form is a property of a relation in a relational database. A relation is in first normal form if and only if the domain of each attribute contains only atomic values, and the value of each attribute contains only a single value from that domain. Examples. The following scenario illustrates how a database design might violate first normal form. Suppose a designer wishes to record the names and the telephone numbers of customers. He defines a customer table which the first column is customer ID. The first column is 123. The second column is 456. The third column is 789. The second column is first name. The first column is Robert. The second column named Jane. The third column named Maria. Third column named surname. The first column is Ingram. The second column is Wright. The third column is Fernandez. The fourth column, telephone number. The first column number is 555-861-2025. The second column is 555-403-1659. The third column is 555-808-9833. The designer then becomes aware of a requirement to record multiple telephone numbers for some customers' reasons. That the simplest way of doing this is to allow the telephone number field in any given record to contain more than one value. So, the fourth column, in the fourth column telephone number, the second column adds another number. Assuming, however, that the telephone number column is defined on some telephone number-like domain, such as the domain of 12-character strings. The representation above is not in first normal form. It is in violation of first normal form, as a single field has been allowed to contain multiple values. A typical relational database management system will not allow fields in a table to contain multiple values in this way. A design that complies with first normal form. A design that is unambiguously in first formal form makes use of two tables, a customer name table and a customer telephone number table. Repeating groups of telephone numbers do not occur in this design. Instead, each customer to telephone number link appears on its own record, with customer ID as key. A one-to-many relationship exists between the two tables. A record in the parent table, customer name, can have many telephone number records in the child table, customer telephone number, but each telephone number belongs to one, and only one customer. It is worth noting that this design meets the additional requirements for second and third normal form. Second normal form. Second normal form is a normal form used in database normalization. A relation is in the second normal form if it fulfills the following two requirements. It is in first normal form. It does not have any non-prime attribute that is functionally dependent on any proper subset of any candidate key of the relation. A table that is in first normal form must meet additional criteria if it is to qualify for second normal form. Specifically, a table is in second normal form if and only if it is in first normal form and no non-prime attribute is dependent on any proper subset of any candidate key of the table. A non-prime attribute of a table is an attribute that is not part of any candidate key of the table. Put simply, a table is in second normal form if and only if it is in first normal form and every non-prime attribute of the table is dependent on the whole of a candidate key. Example: consider a table describing employee skills. Neither employee nor skill is a candidate key for the table. This is because a given employee might need to appear more than once. He might have multiple skills, and a given skill might need to appear more than once. It might be possessed by multiple employees. Only the composite key, employee skill, qualifies as the candidate key for the table. The remaining attribute, current work location, is dependent on only part of the candidate key, namely employee. Therefore, the table is not in second normal form. Note the redundancy in the way current work locations are represented. We are told 3 times that Jones worked at 114 Main Street and twice that Brown works at 73 Industrial Way. This redundancy makes the table vulnerable to update anomalies. It is, for example, possible to update Jones' work location on his shorthand and typing records and not update his whittling record. The resulting data would imply contradictory answers to the question, what is Jones' current work location? A second normal form alternative to this design would represent the same information in 2 tables, an employees table with candidate key employee and an employee skills table with candidate key employee skill. Third normal form. The third normal form is a normal form used in database normalization. Codd's definition states that a table is in third normal form if and only if both of the following conditions hold. The relation R table is in second normal form. Every non-prime attribute of R is non-transitively dependent, directly independent on every superkey of R. A non-prime attribute of R is an attribute that does not belong to any candidate key of R. Untransitive dependency is a functional dependency in which X goes Z. X determines Z indirectly by virtue of virtue of x determines y and y determines z, where it is not the case that y determines x. A third normal form definition that is equivalent to Codd's but expressed differently was given by Carlo Zaniolo in 1982. This definition states that a table is in third normal form if and only if, for each of its functional dependencies, x determines A, at least one of the following conditions holds: x contains A, that is, x determines A is trivial functional dependency, or x is a superkey for every element of A minus x. The set difference between A and x is a prime attribute. Each attribute is an A minus x is contained in some candidate key. An example of a second normal form table that fails to meet the requirements of third normal form is tournament winners. The first column named tournament. The first column is Indiana Invitational. The second column Cleveland Open. The third column Des Moines Masters. The fourth column Indiana Invitational. The second column name year. The first column is 1998. The second column is 1999. The third column is 1999. The fourth column is 1999. Winner. The first column is Alfred Fredrickson. The second column is Bob Albertson. The third column is Alfred Fredrickson. The fourth column is Chip Masterson. Winner date of birth. The first row is 21 July 1975. The second row is 28 September 1986. The third row is 21 July 1975. The fourth row is 14 March 1977. Because each row in the table needs to tell us who won on a particular tournament in a particular year. The composite key, tournament year, is a minimal set of attributes guaranteed to uniquely identify a row. That is, tournament year is a candidate key for the table. The breach of third normal form occurs because the non-prime attribute winner date of birth is transitively dependent on the candidate key, tournament year, via the non-prime attribute winner. The fact that winner date of birth is functionally dependent on winner makes the table vulnerable to logical inconsistencies, as there nothing to stop the same person from being shown with different dates of birth on different records. In order to express the same facts without violating the third normal form, it is necessary to split the table into two. Normalization beyond third normal form. Most third normal form tables are free of update, insertion, and deletion anomalies. certain types of third normal form tables rarely met with in practice are affected by such anomalies. These are tables which either fall short of Boy's code normal form, or if they meet BCNFF, fall short of the higher normal forms in fourth normal form or fifth normal form. Boy's code normal form, or BCNFF, or 3.5 normal form, is a normal form used in database normalization. It is slightly stronger version of the third normal form. If a relational schema is in BCNFF, then all redundancy based on functional dependency has been removed, although other types of redundancy may still exist. A relational schema R is in Boy's code normal form only if for every one of its dependents X determines Y, at least one of the following conditions hold. X determines Y is a trivial functional dependency. X is a superkey for schema R. Note that the third normal form is a database schema design approach for relational database which uses normalizing principles to reduce the duplication of data, avoid data anomalies, ensure referential integrity, and simplify data management. BCNFF, or Boy's code normal form. BCNF is the advanced version of third normal form. It is stricter than third normal form. A table is in BCNF if every functional dependency X determines Y. X is the superkey of the table. For BCNF, the table should be in third normal form. And for every FD, LHS is superkey. Boy's code normal form is a normal form used in database normalization. It is slightly stronger version of the third normal form. BCNF was developed in 1974 by Raymond F. Boyce and Edgar F. Code to address certain types of anomalies not dealt with by third normal form as originally defined. BCNF is a stronger form of normalization than third normal form because it eliminates the second condition for third normal form, which allowed the right side of the FD to be a prime attribute. Thus, every left side of an FD in a table must be a superkey. Only in rare cases does a third normal form table not meet the requirements of BCNF. A third normal form table which does not have multiple overlapping candidate keys is guaranteed to be in BCNF. Depending on what its functional dependencies are, a third normal form table with two or more overlapping candidate keys may or may not be in BCNF. An example of a third normal form table does not meet BCNF is today's court bookings. Today's court bookings. Thus, the first and third row have 1. The fourth and sixth row has 2. 3, 2. Start time. The first row is 9:30. The second row is 11. The third row is 14. The fourth row is 10. The fifth row is 11:30. The sixth row is 15. End time. The first row is 10:30. The second row is 12. The third is 15:30. The fourth is 11:30. The fifth is 13:30. The sixth is 16:30. Rate type. The first and second row is saver. The third row has standard. The fourth and sixth row has premium. The fourth and fifth row has premium B. The last row has premium A. Each row in the table represents a court booking at a tennis club that has one hard court and one grass court. A booking is defined by each court and the period for which the court is reserved. Additionally, each booking has a rate type associated with it. There are 4 distinct rate types. Saver for Court 1 bookings made by members. Standard for Court 1 bookings made by non-members. Premium A for Court 2 bookings made by members. Premium B for Court 2 bookings made by non-members. Note that even though in the above table start time and end time attributes have no duplicate values for each of them, we still have to admit that in some other days, 2 different bookings on Court 1 and Court 2 could start at the same time or end at the same time. This is the reason why start time and end time cannot be considered as the table superkeys. However, only S sub 1, S sub 2, S sub 3, and S sub 4 are candidate keys. That is minimal superkeys for that relation because S sub 1, S sub 5, so S sub 5 cannot be a candidate key. By the way, this symbol means candidate key. In today's court bookings table, there are no non-prime attributes. That is, all attributes belong to some candidate key. Therefore, the table adheres to both second normal form and third normal form. The table does not adhere to B, C, and F. This is because of the dependency rate type court, in which the determining attribute rate type is neither a candidate key nor a superset of a candidate key. Dependency rate type. Court is respected as a rate type should only ever apply to a single court. The design can be amended so that it means B, C, and F. The candidate keys for the rate types table are rate types and court member flag. The candidate keys for the today's bookings table are rate type, start time, and rate type, end time. Both tables are in BCNF. Fourth normal form. Fourth normal form is a level of database normalization where there are no non-trivial multi-valued dependencies other than a candidate key. It builds on the first three normal forms: first normal form, second normal form, and third normal form, and the Boyce code normal form, BCNF. The table should not have any multi-valued dependency. So here's the example of the table. It's a delivery permutations restaurant. The first, second, third, fourth, fifth, and sixth row have A1 pizza. 7 and 8 row have Elite pizza. 9, 10, 11, and 12 row Vincero's pizza. Pizza variety. The first to third row have thick crust. Fourth to sixth row have stuffed crust. Seventh row had thin crust. Eighth row had stuffed crust. 9 to 11 row have thick crust, and the 9 to 12 row had thick crust. Delivery area. First row Springfield. The second row Shelbyville. Third row Capital City. Fourth row Springfield. Fifth row Shelbyville. Fifth to seventh row Capital City. Eighth row Springfield. Ninth row Shelbyville. 10th row Springfield. 11th row Shelbyville. Each row indicates that a given restaurant can deliver a given variety of pizza to a given area. The table has no non-key attributes because its only key is restaurant, pizza variety, delivery area. Therefore, it meets all normal forms up to BCNF. If we assume, however, that pizza varieties offered by a restaurant are not affected by delivery area, then it does not meet fourth normal form. The problem is that the table features two non-trivial multi-valued dependencies on the restaurant attribute, which is not a superkey. The dependencies are restaurant, pizza variety, restaurant, delivery area. These non-trivial multi-valued dependencies on a non-superkey reflect the fact that the varieties of pizza a restaurant offers are independent from the areas to which the restaurant delivers. This state of affairs leads to redundancy in the table. For example, we are told 3 times that A1 pizza offers stuffed crust, and if A1 pizza starts producing cheese crust pizzas, then we will need to add multiple rows, one for each of A1's pizza's delivery areas. There is moreover nothing to prevent us from doing this incorrectly. We might add cheese crust rows for all but one for A1 pizza's delivery areas, thereby failing to respect the multi-valued dependency restaurant pizza variety. To eliminate the possibility of these anomalies, we must place the facts about varieties offered into a different table from the facts about delivery areas, yielding 2 tables that are both in fourth normal form. In contrast, if the pizza varieties offered by a restaurant sometimes legitimately vary from one delivery area to another, the original three-column table would satisfy fourth normal form. Fifth normal form, also known as project join normal form, PJNF, is a level of database normalization designed to reduce redundancy in relational database recording multivalued facts by isolating semantically related multiple relationships. A table is said to be in the fifth normal form if and only if every non-trivial join dependency in it is implied by the candidate keys. Consider the following example. The table's predicate is products of the type designed by product type made by the brand designed by brand are available from the traveling salesman designed by traveling salesman. In the absence of any rules restricting the valid possible combinations of traveling salesman brand and product type, the three attribute table above is necessary in order to model the situation correctly. Suppose, however, that the following rule applies. A traveling salesman has a certain brands and certain product types in his repertoire. If brand B1 and brand B2 are in his repertoire and product type P is in his repertoire, then assuming brand B1 and brand B2 both make product type P, the traveling salesman must offer products of product type P, those made by brand B1 and those made by brand B2. In that case, it is possible to split the table into three. So that's all. I've explained the first normal form, second normal form, third normal form, BCNF, fourth normal form, and fifth normal form. Thank you for listening.